So it says find the initial velocity of the mass if it is released from the equilibrium position and is to oscillate between x equals negative 0.1 and positive 0.1 meters. So we can see straight off that this is going to be a free vibration question because we have no externally applied forces. And we're also going to end up with undamped motion because we have no dampers attached to our mass at all. They're all springs. So to start this off with, I'm going to draw myself a free body diagram of my mass. And from it I should be able to sum my forces to be the mass times acceleration, work out my natural frequency, and so on. So I'm going to say that my mass is going to move in the positive x direction as defined here. So that's going to be the direction of mx double dot. And if my mass is going to move to the right, each of these is going to try and move it back to where it was, so to the left. So they're all going to be this way. Right? And force in the spring is equal to the constant, which for each of these is k, multiplied by the displacement of that spring, which is going to be x, how far the block has moved. So each of these are going to be kx. So we said that this was the positive x direction. So when we sum our forces to be equal to the mass times acceleration, each of these is in the negative x direction, and I'll put them all together, so we've got three of them, so it's going to be negative kx is equal to, this is in the positive direction, so it goes in as mx double dot. So now I'm going to want to rearrange this equation so I have everything on one side. So I can make it 0 equals mx double dot plus 3kx. And if I divide by m, it's going to mean that I end up with a 1 in front of this x double dot. Like that. Alrighty, so now I'm up to trying to determine omega n and the damping ratio. So I know that this equation here has to equal the general form. Alrighty, so we know that the x part here, omega n squared, has to equal 3k on m. And we can rearrange it like that. And we know, oh, I forgot to give you each of the different things, what they were equal to. That's okay. So let's say that k is equal to 40 newtons per meter and the mass is equal to 6 kilograms. So if we substitute that down here, we end up with a natural frequency of 5.48 radians per second. So now we need to determine our damping ratio, and because we didn't have any dampers in our system, you should be able to conclude that it's equal to 0. However, if you want to do it mathematically, you're going to end up with that 2 omega n zeta has to equal what's in front of the x dot part of this equation, and since it's not here, we know that the x dot part is equal to 0. So we end up with our damping ratio then has to be the one that's equal to 0 in that equation, resulting in undamped motion. Alright, so now we just need to work out the initial velocity that's going to make it swing between negative 0.1 and positive 0.1 meters. So we can use our equation for undamped motion for x as a function of time, and we have two options for that. So one of them is a cos omega nt plus b sine omega nt. The other one, you combine them together and insert a phase shift instead. So this one probably makes a little bit more sense to you, and intuitively you can know that that's going to look like just a single sine wave that's going to bounce between positive and negative c. So that's the one I'm going to use, but it doesn't matter which one you pick, they're exactly the same, they're equivalent. Okay, so let's go with this one. So what we know is that at time equals 0, we need to work out what the initial velocity is, x dot. Okay, it also tells us up here at the top that it's being released from the equilibrium position. So that's going to mean that at t equals 0, x is equal to 0. Okay, but we're given this little extra piece of information where it's got to bounce between negative 0.1 and positive 0.1. And from looking at this sine wave equation, we know that the amplitude is c, so it's got to be 0.1 meters. Okay, so now the only unknown that we're really looking for is x dot. However, we're going to have to go through and work out what phi is first to be able to find it. So let's go with this equation and using our first initial condition. So that is that 0 equals c sine, I'll just leave this as omega n because it's going to go away anyway. Alright, equals 0. So 0 is going to equal c multiplied by sine of phi. Alright, and c is our amplitude. We know that's equal to 0.1. So what that's going to mean is if we divide both sides by c, we're going to get that 0 equals sine phi. And if you solve for phi, it actually comes out to be 0. So our phase shift is 0. It's going to be a perfect sine wave. So now we just need to work out what x dot is. And for that we need to take the derivative of our equation for x. So it's going to become x dot equals, so we can leave c out the front, it's a constant. Derivative of sine is cos, write out the bracket, and then multiply by the derivative inside, which is just going to be omega n. So this becomes that. So we need to solve for what x dot is. That's our, question that we're asked to find. So we just need to substitute in. So we said that c has to be 0.1 if it's going to bounce between negative 0.1 and 0.1. Omega n we've already solved for. It came out to be 5.48. Times 0 for time. And phi we said was 0 as well. So this comes out to be 0.1 times 5.48 multiplied by, this is going to come out to cos of 0, which is 1. So that's what we come out with. So that's the final answer that we're looking for. So if you were to plot it, for example, your x is a function of time, this equation here, you'd get 0.1 sine of 5.48 t, which is just going to be a perfect sine wave, something like this. Alright, bouncing between 0.1 and negative 0.1 in meters. Alrighty, so that's the answer to that one. See you next time.